Okay, picture this for a second. Imagine you stumble upon a magical treasure box. But this isn't just some ordinary, dusty chest. It actually doubles whatever is inside it every single day. So on day 1, you pop it open and find exactly 2 gold coins. Cool, right? Day 2, there are 4 coins. By day 3, there are 8, and the pattern just relentlessly keeps going. Now, at first, this sounds like a fun little novelty, but exponential growth is incredibly deceiving, because by day 10, that little box is bursting with over 1,000 gold coins, and by day 20, you are looking at over 1,000,000. Mathematically, trying to keep track of that kind of rapid, explosive growth is a really fascinating challenge, mostly because the numbers escape our ability to wrap our heads around them incredibly fast. So if that treasure kept doubling for, say, 30, 60, or even 100 days, how on earth do we even track that without writing endless pages of multiplication? I mean, just writing out the math for day 50 would literally mean writing 2 times 2 times 2 50 separate times. It would be insanely tedious, super prone to human error, and honestly, just a massive waste of ink. We desperately need a mathematical shortcut to handle this very real-world problem of rapid growth. We basically need a way to compress reality into something manageable. Well, the elegant solution to our massive number problem is what early mathematicians essentially designed as a compression algorithm, and it's perfectly captured by this idea: the language of genius, abbreviation in algebra. Today in this explainer, we're diving into exponents. And look, try not to think of exponents as some complex mathematical chore, but rather as an incredibly powerful, elegant tool. They were designed specifically to take these massive, unwieldy chains of multiplication and compress them down into a clean, brilliantly abbreviated format. It lets us calculate staggering growth in just a few keystrokes. Let's break down the mechanics of how this abbreviation actually works under the hood. Usually you'll see an expression like a to the power of n. If we jump back to our magical treasure box, a represents the base. You can think of the base as the treasure itself. It's the exact number that gets repeatedly multiplied. Then we have n, the exponent, which a lot of people also call the power. The exponent acts purely as a counter. In our scenario, it's the number of days that have passed. It tells you exactly how many times you need to multiply the base by itself. The entire system, the whole shebang, is built on this idea of repeated multiplication. Now, wrapping your head around repeated multiplication is absolutely crucial because it protects us from a very common cognitive glitch. Human brains naturally default to simple, lazy, linear pathways. So when we see a 2 and a 3 sitting next to each other, our brain instantly wants to say, oh, easy, 2 times 3 is 6. But wait, that is the ultimate trap. The golden rule of exponents dictates that 2 to the power of 3 means you multiply 2 by itself 3 times. So 2 times 2 times 2 equals 8. It is the base multiplying itself, doubling 3 times, not the base multiplying the exponent. Recognizing this difference between simple multiplication and exponential scaling is going to be your key to unlocking this whole concept. So what happens when we dive into some advanced special cases? Well, the underlying logic is actually wonderfully simple. Let's start with the power of 1. Any number to the power of 1 is, quite simply, just itself. So a to the power of 1 is just a. If we think back to the treasure box, an exponent of 1 simply represents day 1. The multiplier hasn't even kicked in yet. The factor hasn't repeated. It's just sitting there exactly as it started, written down exactly 1 time. But here is where things get genuinely counterintuitive. This is the famously confusing zero exponent rule. It states that any non-zero number to the power of 0 equals 1. Yes, a to the power of 0 equals 1. I know, it almost feels like a glitch in the math, right? How is it even possible that raising a base to a power of absolutely nothing suddenly gives you the number 1? It completely defies our basic intuition of how numbers are supposed to behave when 0 is involved. To really wrap our heads around this, we just have to reverse engineer the mystery. Let's use 10 as our base. 10 to the power of 3 is 1,000, right? Now let's drop the exponent by 1. 10 to the power of 2 is 100. Mathematically, moving from 1,000 to 100 means we simply divided by our base of 10. Let's drop the exponent again. 10 to the power of 1 is 10. Once again, we divided by 10. Now, if we followed that precise, unbreakable pattern all the way down to an exponent of 0, we have to divide our previous answer, which was 10, by our base of 10, and 10 divided by 10 leaves us with exactly 1. See, it's not arbitrary magic. It is just the pure elegance of a mathematical pattern working perfectly in reverse. All right. It's time to put this genius abbreviation to the test with a bit of a thought experiment. Imagine combining two entirely different exponential scenarios into one massive challenge, kind of like defeating a boss equation. Let's say we need to evaluate 4 to the power of 3 plus 2 to the power of 5. It looks a bit intimidating at first glance, right? Combining different bases and different powers into a single line of math. But remember, because exponents act as compressed files holding massive chains of multiplication, the mathematical order of operations, good old PEMDAS, dictates that we must unzip those files first before we try to add anything together. So unpacking 4 cubed means 4 times 4 times 4, which gets us 64. Next, we unzip 2 to the power of 5. That's 2 times 2 times 2 times 2 times 2, which gives us 32. Now that the abbreviations are fully unpacked, we can comfortably add them up. 64 plus 32 gives us a final result of 96. So by systematically uncompressing the math first, even complex, multi-base equations become a total breeze. When we pull all of these rules together, the power of 1, that magic zero rule, avoiding the trap of simple multiplication, they form a perfectly logical system, like a cheat sheet for reality. But there's one crucial little detail to always watch out for, especially when negative numbers enter the mix. Think about a -2, fully enclosed in parentheses and squared. Those parentheses act as an anchor. They tie the negative sign directly to the base itself. That means you are multiplying -2 by -2, which cancels out the negatives and gives you a positive 4. If those parentheses weren't there, the math would behave entirely differently. It's a tiny structural detail, but actually scratch that. It's a massive detail that completely changes the trajectory of your exponential growth. So we've basically learned how to bend massive, unruly multiplications to our will, turning astronomical growth into simple, elegant notation. As we wrap up this explainer, I want you to consider this truly mind-blowing fact. If you could take a standard piece of paper and fold it in half just 42 times, its thickness would grow exponentially until it reached literally all the way to the moon. No joke, the moon. That is the sheer compounding power of exponents. So I'll leave you with this to chew on. Where else in your daily life is exponential growth hiding in plain sight? From viral social media trends and the processing power of your smartphone to compounding interest in your bank account, this math literally shapes our reality. Keep observing, stay curious, and we will catch you next time.